Hello, for today's video lecture, we're going to be talking about area moments of inertia via the method of composite parts. So, as an alternative to using integration to find area or mass moments of inertia, we can use lookup tables along with the parallel axis theorem to find the combined moment of inertia for a composite body. In this way, we can skip all the integration that we did in the previous sections and instead use the work of others in that table as a kind of shortcut. So this is going to be very similar to the method we used to find the centroid or center of mass of a composite body. And even though they have the same title, they are going to have slight differences, although they are both going to be table-based for all of this. So the overall process is going to be as follows. So first, we're going to want to break our composite shape down into simple shapes that are in the lookup tables. So we might have some body that is a bunch of pieces. We want to try to find circles, rectangles, triangles, other kind of simple shapes that make up our overall body. We want to look up the moments of inertia for each individual shape using the moment of inertia tables. We're going to use the parallel axis theorem to adjust the moments of inertia to a common origin point. We're taking the moment of inertia about. And then we simply need to add the adjusted moments of inertia together to find the overall moment of inertia for the combined shape. So with this, let's start with the first step. So the first step in finding our combined moment of inertia is to break our complex shape into simple shapes that are in our moment of inertia tables. So the shape below, for example, I might break this into three pieces. I've got a semicircle over there on the left. I've got a square or rectangle for shape 2. And then I've got a triangle on that bottom right corner there. And those holes or cutouts, we can count those as negative areas. So do pay attention to the holes or cutouts or subtracting area as a way to work with this as well. So another useful portion of this is it might be useful to identify an axis and an origin point at this point to use in calculations. Often we're going to need to find the centroid and we need to have a set of axes that we're working with to find the centroid as a starting point. So next, you're going to create a table of values to keep track of the various pieces. There's a lot of numbers that you're going to keep track of along the way. So this table here below is an example. So each row is going to be used for one of the pieces or one part. So I've got shape 1, 2, and 3 in my diagram. Those should correspond to row 1, 2, and 3 in my table. And then each of the columns are going to vary from problem to problem, but they're generally going to follow the same format. We're going to need to know the area of each shape. We're generally going to need to know the x and y coordinates of the centroid of each shape. We're going to need to know IXC and IYC. These are going to be the values that I look up in the tables. These are going to be my adjustment distances with the parallel axis theorem, and these are my adjusted moments of inertia after adding the plus AR squared values from this piece here. So filling out this table is the biggest piece of work that we're going to be doing in using the method of composite parts. So filling out the table is kind of the problem itself. After determining the area or mass of each piece, area in this case, the next step is to find the overall the centroid location of each piece as well as the centroid location. And so we're generally going to be taking the moment of inertia for a composite body about the overall centroid location. This is because with bending or torsion, we need to be taking the moments about that point. And so because of that, we need to know where that overall centroid is. And even if we are given that overall centroid location, we're still going to need to know where the centroids are for each of the individual pieces that I'm working with in this. So in my previous table up here, for example, X bar and Y bar, that'd be the overall centroid of my shape. X bar and Y bar up here, this is the centroid of shape 1. So X bar, Y bar for that semicircle, X bar, Y bar for my rectangle, X bar, Y bar for my triangular cutout up here. So this is the same as calculating the centroids for using the method of composite parts we talked about earlier in this section. And that's why it's important to have an axis at this point. This X bar and Y bar locations, these all need to be with respect to a common point. So once we have that, you're going to need to look up and calculate the moments of inertia about their individual centroids. So each piece, we're going to have the moment of inertia of a semicircle, and we are sometimes going to need to adjust the orientation to match the table match the orientation of the piece to the orientation in the table so that the two match. An example of this is I've got my shape down here. If I look at the moment of inertia table, I'm going to see that this is the semicircle that is available in the table. So there is a 90-degree turn. So this is on its side. This is kind of upright. And when that happens, you're going to want to switch. So for this, if I want to know what Ix is, I'm actually going to use the Iy value because the X and Y are kind of switched from the diagram to what I have in my problem. So keep that in mind. You may need to switch the X and Y axes if the table diagram does not match the diagram you're working with for your problem. And then the parallel axis theorem states that IXP equals IXC plus AR squared. We talked about this in the previous section. Just a reminder, this is the area moment of inertia about any point P is going to be equal to the area moment of inertia about the centroid plus AR squared. So A is the area of the shape. This is the area of the piece that we're working with. And then R is going to be how far I need to move to get from the x-axis that I have in my table to the x-axis that I need to use for my problem. So the R value in this, so the plus AR squared, the R value here is going to represent the adjustment that we're making. So if I'm going from, for example, in shape 1, that is going to be my semicircle. I need to figure out how far is it from the y-axis, so this is adjusting IY, from the centroid of the semicircle over to the centroid of the composite body. So I need to adjust each of these to the overall centroid location. So semicircle to overall centroid, it's going to be a horizontal distance for y. And then if I am looking at my rectangle, it's going to be this distance here. So center of the rectangle to the overall centroid. And for my triangular cutout, centroid of the triangle to the centroid of the overall shape. And so with this, it's important, remember that this is how far the axes are adjusted, not necessarily how far the point is moving. If I am adjusting Ix values, it's always going to be a vertical distance for this. If I'm adjusting Y values, it's going to be a horizontal distance for this because it's how far the Y-axis moves left to the right. And if I have Z values, so these are going to be the polar moments of inertia, those are axes pointing out of the page. That would be the diagonal value that we have in this. Regardless of direction, we really just count these as positive. So it doesn't matter up, down, left, right. We square the term so they all wind up positive in the end because it's plus AR squared for my adjustment. So once you've figured out your R values, how far you're moving the axes in each of these cases, there are going to be adjustments to the Y values, adjustments to the X values separately. So that's why we have Rx, that's how far I'm adjusting all the X axes, Ry, how far I'm adjusting all the Y axes. We need to plug those into the table. We are going to do our adjusted values using the parallel axis theorem. So whatever IXC was from our table, so for shape 1, I'd have something IXC over here. I'd do plus area times Rx squared. That is what gets plugged in for my Ix adjusted. Iy adjusted would be IYC for this first shape over here, plus area times Ry squared. That gets plugged in over here. Once we have all of these Ix and Iy values adjusted, then we can add them together. So everything in the Ix adjusted column gets added together to find the Ix for the total shape. Everything in the Iy adjusted gets added together to find the Iy for the total shape there. We cannot add together our moment of inertia values until we do this parallel axis theorem adjustment process because all of these Ix and Iy values are all taken about different points, and so we cannot add them together. All right, so that's all we have for this method. Thank you for watching, and I hope to see you again.